Great, thanks Chris. So yeah, I'm Michael Williams. I'm a PhD student at the Institute for Gravitational Research at the University of Glasgow, and I'm going to be talking about importance nested sampling with nessai. And if you have no idea what I mean by nessai, don't worry about that. I'll get to it in a bit. So I'm talking about nested sampling, so obviously we're going to be talking about gravitational wave inference and focusing specifically on compact binary coalescence. And as people have alluded to already in the previous talks, in gravitational wave inference, we want to determine the parameters of a signal via Bayes' theorem. So that is, we want to estimate a posterior distribution in terms of the likelihood, prior, and the denominator here, which is the evidence or the marginalized likelihood. And this posterior distribution will typically be something that's sort of 15-dimensional and contain things like the masses, spins, orientation on the sky, and the likes. And the way we do this is typically using stochastic sampling techniques, such as Markov chain Monte Carlo or nested sampling, and I'll be focusing on the latter. So in nested sampling, what we're really interested in is the denominator here in Bayes' theorem, so the evidence or the marginalized likelihood. And this is typically difficult to compute because it is an integral over the parameter space. And this means that it's not easy to do, and that's why we have to resort to something like nested sampling. And in nested sampling, the core trick to make the evidence tractable is to rewrite the parameter space in terms of a one-dimensional integral, as shown here, that includes this variable x, which is called the prior volume. And this is defined between 0 and 1. And this just allows us to actually compute the evidence because it's 1D and easy to approximate. So generally, the easiest way to sort of try and understand this is pictorially. So if you imagine you have some two-dimensional parameter space, and the prior here is the black box, and we have some likelihood surface here shown with the blue contours. The prior volume just describes this whole space. So a prior volume of 1 indicates the entire prior, and then as we reduce the prior volume, we're considering smaller and smaller regions of the space. And in nested sampling, those spaces are defined in terms of the likelihood. So we consider different contours in likelihood, and we start from the entire prior and shrink down. And so it's considering increasing likelihoods. And as we do that, we can approximate the area under this curve, and that's just the evidence. So how do we actually do this? So in nested sampling, what we're going to start with is we're going to start with the entire prior. So we're going to start with some samples from the prior. So this would be a prior volume of 1. And what we're going to do is we're going to consider the worst point. So that's the point with the lowest log likelihood. And then we're going to want to replace it with a point that has a higher log likelihood. And we're going to do this over and over until we eventually have shrunk the prior volume sufficiently that the estimate of the evidence converges. So we can show an example of this here with this animation. So the red crosses here are being replaced one by one and they're being discarded, and then they become blue, and then they're being moved in and replaced closer and closer to the maximum likelihood, which is 0, 0 in this case. So if you pick a point, you'll see that as it shrinks in, it's going to be discarded and replaced. And as we're doing this, we're computing the prior volume, and you can see here the curve is evolving on the right-hand side. And as we're doing this, we're improving our estimate of the evidence. So the challenge when doing this is actually, how do we draw these new points? So when we have a point that we've discarded and it becomes a blue point here, how do we draw a new point to replace it? And this is where nessai comes into play. So nessai stands for nested sampling with artificial intelligence. And the core idea in nessai is to train a type of machine learning algorithm called a normalizing flow to learn the likelihood contours during the nested sampling run. So if you think back to the previous animation, we had some red crosses. The blue dots here are the equivalent of the red crosses, but for a slightly different likelihood. What we want to do is we want to learn a contour that contains these points and allows us to sample from within it. So in this case, we learn this yellow contour using the normalizing flow, and then we can sample new points directly from it. So this allows us to directly draw new samples within the constrained region. And these samples need to be distributed according to the prior. So We showed in our paper originally that we could apply nessai to gravitational wave inference, specifically for binary black hole injections. We considered 128 injections that were 4 seconds long, sampled at 2 kilohertz in a 3-detector network, and with a median SNR of around 16. So these are reasonably loud events, but there are some quieter ones as well. So we performed the inference with nessai, and we compared to Dynasty, which is another nested sampler that has been used extensively by the LIGO-Virgo collaboration for a lot of the inference in their recent analyses. And what we compared, the number of likelihood evaluations. So this is an indication of how efficient the process of proposing and accepting or discarding new points is, and the warp time. Obviously, the warp time isn't the best thing to compare because it is very dependent on exactly where your jobs are being run, but it does give us a ballpark sort of estimate of the sort of speed ups we might expect. So with nessai, we found roughly a 4 times improvement compared to Dynasty in terms of the number of likelihood evaluations, and that translated into roughly just under a 3 times reduction in the total runtime. However, there are some limitations in nessai, and this is what we want to address with this new work. So in standard nested sampling, we need points that are distributed according to the prior within that likelihood contour. And this forces us to include rejection sampling to make sure that the points are correctly distributed. And this is actually a significant bottleneck in nessai. So if we have a look at the pie chart here on the right-hand side, you can see that just over 50% of the time is spent evaluating the likelihood. So that's the process of once we have the points, checking whether we should accept them or reject them. Just under 10% is spent training the machine learning. And actually over a third of the time is spent drawing the new points, and the majority of that is this rejection sampling. Because as we increase the dimensions, it can become quite inefficient. So this is one of the things we want to address. And the other is sort of a more fundamental thing. Most machine learning algorithms are designed to work with batches of samples, and this includes normalizing flows. However, nested sampling is inherently a serial process. If you think back to the animation I showed, points were being replaced one by one as the volume shrunk. So these are 2 main points we want to address. And the way we're going to do this is with importance nested sampling. So our aims with these changes are to remove the requirement for samples to be drawn from the prior. We want to design an algorithm that uses batches of samples that's better suited to the use of machine learning. And we want to actually allow samples to be added in any order. So not just strictly increasing in likelihood. So if you think back to the first animation, the points were shrinking from lowest likelihood to highest likelihood. We want to remove that constraint. And our method for doing this is going to combine elements. 2 minutes?
2 minutes.
Great, thanks, Chris. We're going to combine elements from multi-nest, another nested sampler that has used importance sampling, from diffusive nested sampling, and from sequential Monte Carlo. And what this is going to give us is it's going to give us a slightly different view of nested sampling. Rather than thinking about shrinking as a sort of serial process one at a time, we're going to think of a set of different levels or distributions that, when we consider them as a whole, approximate a distribution which gives us the evidence and posterior samples. I think the best way to understand the difference is to look at another animation. So here on the right-hand side, we have our version of nessai that uses importance sampling. And you can see here, points are being added in batches in these different colors. And what each of these batches represent is an iteration. And at each iteration, we've trained a normalizing flow to draw these samples. And basically all we're doing is drawing samples and directly adding them to our overall set of samples. And you can see as we do that, we get closer and closer to the maximum likelihood. And so what we end up with at the end of this is a set of n normalizing flows, which are essentially distributions, which we can draw from to get our final samples, and then we can get from that the evidence and posterior samples. So we revisited the analysis we did for our original paper for nessai, and we applied this new version of nessai, the importance nested sampling nessai, and we found that it significantly reduced the cost of performing the inference and sped it up. So this new version is about 5 times faster than nessai and about an order of magnitude faster than dynasty, depending on whether you're considering likelihood evaluations or the actual wall time. So now you can see we're actually down to around 2 hours to perform inference. And I'll be 2 secs. And just now, if we look, we can see now that most of the cost is actually just the likelihood, and performing the rejection sampling is a minimal cost. So with that, I'll just leave us here with a summary.
Thank you very much, Michael. Please, people, add questions to the Q&A if something is coming up in your head at the moment. I'm related to this work, so I shouldn't be asking questions, but I guess I could ask, is that last pie chart telling me that you're basically there's 75% of your costs is likely, or 76. You can't really speed this up much more. Is that a fair statement?
I think you can't really speed it up with modifications to the algorithm. You'd now look at speeding it up by, for example, parallelizing the likelihood evaluation. So because we're working with batches of samples, it's very easy to parallelize the likelihood. So if we scaled this to work on more cores, we could reduce this cost simply by parallelizing it.
And then beyond that, we have a question. In the last pie chart, the other part increased in size significantly, less than 1% to 8%. Do you know the main reason for that?
Yes, so I'm sort of glossing over one of the details here, which is that as we do this process of adding samples to the overall distribution, we need to update the probability of all the existing samples. So that means samples that we drew from the very first iteration, every time we add a new flow, we need to update their probability. And that requires us putting all the samples through all of the normalizing flows, and that has a cost associated with it.